Welcome to today's webinar, the Kluba webinar about design of steel constructions according to Eurocode 3. This is part 1 of the webinar today. We will model a steel construction, define some loading and obtain the load combinations. Next week, same time again on Thursday, we will perform the stability analysis, define imperfections and perform the design checks in accordance with Eurocode 3. So depending on your needs, you can either register for both or just watch one of the webinars. My name is Gerlinde Schubert. I will present the webinar today, and my colleague Wieland Götzler will answer all your questions that you might have during the webinar. To ask your questions, please use the chat option in the control panel of the GoToWebinar software, and you can hide the control panel by using the orange arrow button up here, so just in case it gets in your way. So as I said already, we will model a steel construction today. On the right hand side you see the picture. This is our goal. This is the simple construction that we are going to design. We will define self-weight, imposed loads and wind loads, and therefore we will use load generators. So we will define area loads that are automatically converted into member loads, and we will use a generator to create wind loads in accordance with the Eurocode 1. Finally, we will combine these loads, so we create load combinations and result combinations. This is also an automatic tool, and we do it today in accordance to the Eurocode 0. So I'm going to show you the final model. This is the final structure modeled in RFEM. This is our finite element software. We are going to build a steel platform for a silo with presumably some fillings in it. We do not use RFEM today. We are going to use R-Stab. This is our structural member analysis software. And the user interfaces of both RFEM and R-Stab are nearly identical, besides that you can model surfaces and solids in RFEM. Obviously, in R-Stab, we model the platform without the silo, but we are only interested in the steel construction. And we just enter the loads that are arising from the silo. So we are already getting started with the modeling part. So I'm switching over to a blank R-Stab. So as you see already, so the buttons up here and everything, the appearance is the same as RFEM, but this is here a member analysis software. So I want to create a new model. So I've pressed this button up here, new model, and I want to I give it a name, steel platform. I want to design a 3-dimensional structure, and I want to create load combinations and result combinations automatically in accordance with the Eurocode 0. And I'm not using a specific national annex today because you are coming from over all the world. So I'm just using the recommendations of the Eurocodes. Okay, I just confirmed this, and the main view is coming up. So the first frame that we are going to model is in the XZ plane. So here you can switch in between the different work planes. We are right now in the work plane XZ. This is where we start with. So, and I want to just adjust you can, hold on, tools, select work plane. You can also go in here and you can change the work planes in here. You can change the origin and so on. So all these options are here. And in here, I want to open this option, work plane, grid snap, object snap. I want to adjust my grid snap settings. So just to show you these options here. So we have a grid which is using 1 meter spacing in between. This is okay for my model because I'm just having whole meter numbers, but what I want to activate is the dynamically according to the size of the model option. So my grid is small at the beginning, but it's rising as I model my structure. So we already get started. We define a member. So I'm going to create a free continuous member. This one here. I have to define a new cross-section, create a new cross-section. So I'm going to the create new cross-section. And this is what's opening up. I want to get something from the library. This is the button up here, or here are some shortcut buttons. You can directly go to IPE or AGA, whatever you want. Just to show you the library, I open it. We have many cross sections predefined, and I'm going to choose a rolled one, an IPE cross section. So I click on here and the library is opening, and there is a huge amount of different cross sections, and to filter this a bit, I go to the standard group European, and I want to define an IPE, and I'm going to use an IPE 220, this one here. So this is the material. This is okay as it is. I just want to go in and change what you can do here. To show you what you can do here, here's a library again. You can open the library, and here you have all the different steel, or you can change to concrete, timber, whatever you need. We use metal and steel today, and again the standard group from Europe, and we use steel S253. This is okay. I confirm this and click OK to close all the dialog boxes that were open. And now I move the mouse and can start creating my member by just clicking on the main graphic. So we design the first frame. So I start from 0, 0, 0, click with my left mouse button, move the mouse up to the point 0, 0, -3, so just upwards in that direction. Click again, and the first member is created. I zoom in a bit. And because I have chosen a continuous member, it's still on my mouse, and I can define straight away the next point, which is 4 meters in the x direction. So 4, 0, -3 is the next coordinate. So I click on this, and I go down to close, to finish up with my frame. I move down to 4, 0, 0. So now I click right to finish, and I click right again to close the whole dialog of creating members. When I go just with my mouse on top of the members, you see a red arrow here. This is telling you the direction of the local axis, and you see now it's going upwards here and it's going downwards on this side. So when you want to change the direction of the local axis of the member orientation, you just click right on the member, and you have it in the context menu available, reverse member orientation. And this is what I want to do. I want to have both columns member directions upwards. So this is our first frame being ready already. So we are going to define some nodal supports. This is here, new nodal supports. I open this, and the default one is okay for us, but I want to show you the dialog. So we are defining a hinged support. So the 3 translational directions are fixed, and rotation about the x and the y axis are allowed. So I confirm this, and now I click on the 2 nodes where I want to define the nodal supports. I click right to finish this up, and this is our first frame with nodal supports. And now to save some work, I'm going to copy the first frame. So instead of doing the same again, I'm selecting everything that I've did, and use the move and or copy button up here. And I'm going to copy this just once and in the Y direction about 4 meters. So I click OK, and now I have 2 of the frames available. And in between the 2 frames, I'm going to define beams. Therefore, I do not use the free continuous member. I'm going to use the single members now, because it's quite clear, I think. So I'm going to define a single member. And this time we want to use a different cross-section. So I'm creating a new cross-section. And I can use the shortcut here. It's again an IPE I want to use. It's the IPE 160. I keep the same material and confirm with OK. So the cross-section is defined. I want to also define some member hinges at the member start and end. So I'm going to define a member hinge. And this dialog opens up. And this is what we want to do. We define member hinges that are free to rotate. So we want to make the degrees of freedom free about the weak and the strong axis of the member. So again, I use the default, click OK, and I want to use the same member hinge at the end of the member. So I just choose it from the drop down. So this is member hinge number 1 that I've defined. So OK. And I want to define a beam from the 0 point at roof level here to the frame that I've just copied, so to the coordinate 0, 4, -3. I click OK and click right to close the creating member dialog. Again, I use the copy option. So I select the beam that I want to copy. I go to the move and or copy button, and this time I want to create 4 new beams, and it's not in the Y direction, it's in the X direction with a space of 1 meter. So this is me done with creating the beams. And now what happened? The girders up here that I defined earlier are split into 4 members now. This is because new nodes were created here, and this is automatically splitting the members. Later, for the design, it is important for the software to know that it's still acting as one girder, as one beam. So what I want to do is defining a set of member. So I'm selecting these 4 members, click right on it, and create a set of members. So I call it girder 1. Here you see again the member numbers that are inside the set of members. And I click OK. And I do the same with these beams at the front here. So again, create set of members. This is now girder 2. You see the list of member numbers here. Confirm this. And when I change to the wireframe model, you see that the software created kind of a frame around the members, and this is indicating the set of members. So now, back to the solid display. That's a bit nicer. I'm going to copy the whole thing. So what I want to select is this part of the other way around. When you go from right to left, then you select everything that you are crossing. And I can use the copy option again, or you could use copy, but you can also use drag and drop. So I can just take this by clicking with the left mouse button and can move it everywhere. And when I use the control button as well, then I can easily copy it. So I select it, I press my control key on the keyboard, and I move the whole thing. I copy it and attach it to this point. That's me done with copying. That's a different way of copying things. It's quite easy. And we do the same again. I select it. I press the control key on my keyboard. I get the structure with my mouse key and copy it over here. So now, back to the wireframe model, you see that also the set of members were copied. And you noticed already the table down here. Everything that I model is saved also in the tables. So the notes, the materials, the cross sections, and so on. And also the set of members are here. And it just copied over the same name. So what I want to do is I want to rename this. I just give it different numbers, further 3 and 4. So we are already quite far. I reduce the size of the table, go back to the solid model, and we need some crossing braces now. I'm going to define in the first field some crossing braces. Therefore, I again define a new single member. And again, I define a new cross section. This time I want to use an angle, so I could go on here, import rolled cross section angles, and I want to choose a 60 by 60 by 6, this one. Same material is used again. I click OK. OK here, and this is not a beam. I want to define a tension member. So this is a truss member, but only coping with tension. So you can't define any member hinges because this is implied by the truss or by the tension member already. So there are member hinges at the start and at the end. So I click OK and just click here and there. This is my first member of the brace and repeat single member. So when you right click, you stop some things you do, and when you right click again, you can open a context and you can repeat the previously done. So it's the same member, so here and here. And I click right because I finished defining members. Okay, I want to copy this bracing on the other side. So I select both using the control key on my keyboard, and I can do the same again. So I press the control key, use the left mouse button and move the bracing around. I copy it and attach it finally to the support at the other end here. So the last thing we have to model is the opening and the platform to hold the silo. So remember, I did show you the RFEM model at the beginning. So around here we have a silo, and of course we need to model the opening and some additional members where we define later on the loads arising from the silo. So I'm going to select these 3 members and I want to divide them. So when I click right on them, I have an option, divide member, and I can either define how many nodes I want to have in between, or I can also define a distance from the member start or from the member end. And I'm going to define 1 meter from the member end. I click OK, and you see what happened. It did split the members. And I do the same again. They are still selected, so I just right click on one of them and again divide members with a distance, and this time I define 1 meter from the start. Okay. The members in the middle, they are not needed, so I select the 3 in the middle and delete them. Delete member. We define now new single members with again a different cross section. So I am going to create new cross sections. This time it's a U-shaped member, a U cross section I want to define, and it's the U220. Okay. I have to change back to beam and I want to define the member hinges. I'm using the type 1 member hinge that I've already defined, so I don't have to create a new one again. I can reuse the type 1 that I've defined already. So, okay. So I'm going to define, just notice that I did something wrong because I did not want to delete all 3 members. I only wanted to delete really the center one. I need the other ones. So I've just used the back button, the undo button, and I'm going to delete only the 1 member because I have to keep them, obviously. Yeah. So again, the new single members, and we will see if, no, it forgot because I undid something. So I have to create again the U-shaped cross section. This is quickly done. U220, same material again. Okay and okay. I changed to beam and the member hinges. Okay. And now I'm going to define U-shaped cross sections from here till here and from here till here. So, and what I really want to double check that the U-shaped, and I want to have the back of the U pointing to my opening. So this is okay on this side, and it's also all right on this side. I'm going to change the cross section of these members here. I want to have this as a U-shaped member as well. So I double click on it, or you can again use a right click and edit member. I'm going to, now it's already defined the cross section I want to use, so I just have to go into the drop down and change the cross section. That's okay. And again, I want to double check whether or not the back is pointing to the opening. So it's okay with this member, but on here it's the wrong way around. You could change the member axis direction, but that's not what I want to do because I want to keep local axis directions all in the same direction. So I'm going to select this, click right on it, edit the member, and you can rotate the member. So I'm going to rotate the member, click OK, and now I have what I wanted. The back is pointing to the opening. Okay, we have to assign some member hinges. So I reduce the size. There is a different way to not define, but to assign or insert member hinges. When you go to insert, to model data, you have all the things available here, and you have the member hinges here. You can assign them to members graphically. That's what we want to do. So I want to assign the type number 1. It's the same member hinge I want to use. It's defined already, so I just choose it from the drop-down list. I click OK, and now I select the members where I want to assign the hinges. It's here and it's here. That's me done. No, I did not confirm it. Again, to model data, member hinges, assign members graphically, choose the hinge and select this and select, and I have to confirm this here with OK. And now you see the white balls. I have now assigned some member hinges here. I define now sets of members again to make sure that they are connected for the design later on. So I'm going to define sets of members for these 3 members. This is create set of members, and I call it opening 1. This down here, right click, create set of members, that's opening 2. Okay, and these 2 as well. This is opening 3. And on this side, it's opening 4. Okay, we double check just by going to the changing to the wireframed model. You see all the boxes around the members that are displaying, representing the set of members. So this is us done. We have the model is created, the structure is ready. This is our steel platform. We have created continuous members, we have created single members, we have defined several cross-sections, we have used beam members and tension members, we have defined supports, we have used copy options in different ways, in different versions. We have divided members, deleted some. So when you use the control key on your keyboard, you can rotate the structure and press the mouse wheel, you can rotate the structure. So this is us done with the model, and we are now going ahead and define some loading. We have up here, we have the button new load case. So far we haven't defined any load case, and when you don't have a load case, you cannot define any loads. You always need a load case where the loads are assigned to. So I'm going to define a new load case. It's opening up and it's kind of predefined a self-fade load case here for me. The self-fade is active, the action category is set to permanent, and I'm just choose a name from the drop-down list, which is self-fade. I click OK and the self-fade is defined. Before I define any loads, I'm just going to calculate this load case to double check if everything is working all right. It's not only calculating, it's also doing a plausibility check, and you see here that checks for, of course, for stability. And it says me now the model is unstable, and this is due to the tension members, to the bracing that we have defined. They're failing in one step and they are gone, and the calculation is not possible. When you go to the global calculation parameters in here, calculation parameters, the button up here, I open this. We have some special options for tension members. You have some exceptional handling here, and I activate this. I activate this, and I want that the failing members are removed individually during the iterative process. So it's not all the tension members are failing in one step. So they are failing step by step, and this is how the calculation is possible now. So that's just due to this kind of special load case that the loads are just coming, it's just acting in a vertical direction. It's not, if you would combine it with some loads in the horizontal direction, we wouldn't have the same problem. But here, and now I double check, the calculation is working. Yes, you see now the deformation, the global deformation is 0.5 millimeter, just self-weight, and you also see the failing tension members, which are colorless now. Okay, so now we can go ahead, we double checked our model, and we can go ahead defining more loads. I want to generate loads now. I want to define area loads and convert them into member loads. Therefore, we go to Tools. Further down, you have Generate Loads. And in there, you have from area loads defined via a plane. So I choose this option, and a dialog opens up, and it looks massive at first. So you have a perpendicular plane. We want to have vertical loads defined. So in the Z direction, we want to use the local coordinate system, and the load distribution is uniform. You could have some linear variation and so on. And here is the added field for the magnitude. So we have 0.3 kilonewtons per square meter, just an additional loads from the floor. And here I have to define now the area where I want to define the surface load. So I can select this graphically. So I go on Select Corner Nodes, and I can, like a polygon, I'm going to select the corner nodes of my area. So I start here, first node, and you see the mouse is hanging on it. So I'm going along here, this node, on here, over here, and close the area. Now you see which members are selected. And I don't want to have the loads acting on the girders. I just want to distribute the loads onto the beams. So I'm going to exclude some members from the conversion process. So I'm saying that all members parallel to the member I'm now choosing are excluded. So, okay. And you see now that all members that are parallel to the member number 30 are excluded, so they are not selected. You don't see the red color anymore. So here's a drop down. You're allowed to define several areas. So it's not restricted to one area. So I'm going to use this again and select the rest of my needed area. So I select again an area from here over here, and close the area with the first node again. You see the selection is extended, but you also see that again the parallel members are excluded. This is what I've selected earlier here. So I think I did everything I needed. So it's perpendicular, it's the magnitude. I've defined my area, and I can show you again, you have two areas defined. So they are both in the drop-down. I have excluded some members, and so I just click OK. And now I get a summary of what I did. So it's summarizing for me the loads that I've defined, and yeah, it's converting them into member loads. I click OK, confirm this, and this is now what I did. And you have the option, so when I double click on it, the dialog opens again and I could change things. And when I right click on the load, I have the option to display them separately. So instead of seeing the area loads, I can display them separately so that I see the member loads. They are still connected. So still all the information is saved. And when I click on them, this is still a generated load. There is another option. I could also disconnect them. But this is a permanent disconnection. So when I do this, I do it now, they are not connected anymore. Instead, when I double click on one, it's really a member load. So be careful with this. It's nothing you can undo later on. I can undo now because it's just one step. But if you do this, you never get your generated area load back. So I keep the area loads because I want to keep all the informations. Okay. So we defined the loads for our self-weight load case now. The area loads, we have to define some additional loads for the silo. So here, just remember, I can show you in RFEM again. Here is our silo, and we have to define some additional nodal loads to address for the silo. So back to RStab. I have to divide these members just in the center. So this time I can use the option divide members, and when I have one intermediate node, it's automatically created in the center then. And I'm going to define a nodal load. This is here, new nodal load. And I define a P set of 2 kilonewton. Exactly here. Hold on, I changed to the wireframe model. Here and over here. Yes. Okay, a right click to finish this. And now we are going to define another load case for the imposed loads. And to save a lot of work, we are not creating a new blank load case and define everything from the start again. We are going to copy the load case that we have just created. So I'm going into the Edit Load Cases and Combinations dialog. Here we will go into this dialog quite a few times today. Here you have also the load combinations and result combinations later on. I'm going to copy this load case. Instead of creating a new load case, I'm going to copy it. It's this button here. Copy. I switch off the self-weight. I change the name, imposed loads, and I change the action category to imposed. All the loads are copied as well. It's not only copying the load case, the definition of the load case, it's also copying the loads, and this is the important bit here. So I click OK, and you see the loads are copied as well, and I just have to change the values because the loads itself are the same for the imposed loads. So I'm going to edit my generated load. I double click on it, and this is now it's good that we have saved all the information of the generated load, because now I'm just going to change the magnitude, change it to 2.5 kilonewton per square meter, and that's all I have to do. All the other definitions are still valid, and I click OK, confirm it, and it's automatically converting to the new member loads. I also want to change the value of the nodal loads. It's a bit tricky to pick them graphically, as you see, because of all these member loads. And there are different options. You can, in the data navigator, we have loads. Here is loads, and here you have the load case 2, and here you have nodal loads. This is one option to define to edit the nodal loads, so select them easily. So I could just click on them and it's added nodal loads, and it's opening all of them, all 4. They are assigned to these nodes. Or different way to do it is again the table. In the tables you have the model data, you have the load cases and combinations, and you have the loads. And in the loads you have nodal loads, member loads, and so on, and the generated loads as well. And when I want to change the nodal loads, I can simply change the value here in the table. I change it to 9 kilonewton, and that's all I have to do, and you see it in the graphic, the 2 kilonewton changed to the 9. Okay, that's us done with the load case 2 imposed loads. This was quickly because we copied our first load case. Now we are going to define a new load case for the wind. So this time I can open the added load cases and combinations dialog again and can create a new load case here. I change the category to wind and also select a description here, wind in plus X direction. So that's all I have to do here. And we are going to use a load generator for this. You find it here when you go to Tools, Generate Loads. Here we have been here already. We have used this option previously. Now we are going to use from wind loads. And you have different options here. You can define wind for the vertical walls. This is what we are going to use today. You can define wind for roofs, for different types of roofs, and you can define wind for a combination of walls and with the roof. We are going to define wind for the vertical walls in accordance to the Eurocode. Here now you have quite a lot of annexes, national annexes available. We are, as I said at the beginning, I don't want to be specific to any country today, so I'm going to use just the recommendations. But if you, for example, use the national annex for France, you have informations like the wind zone. You can go on the information button here and you will see a wind zone map with the regions and the colors, and this is the case for Germany as well. You have a wind zone map and so on. This is obviously not the case when I don't use any national annex, and I have to choose things by myself. So I'm going to define a wind velocity of 25 meters per second. I have a structure height. I know it, and this very simple structure, but you can use this little arrow here and you can measure your height. So I go to measure. I reduce the size of my table and just click on 2 nodes to measure my heights. So it's 3 meters. And I'm going to choose a category 2 here. And what we have to do, we have to define the base geometry. So I'm going to select 4 nodes, the 4 corner nodes of the base. And I have to select the 4 corner nodes in the roof level. So again, select all corner nodes of the roof, and I select them all. And I want to exclude again the beams and girders. The wind will act on the columns only. So I'm going to exclude something again. So I exclude members that are parallel to this one, and I'm excluding members that are parallel to this one. So the wind is acting on the columns only in our example. I click OK, and here you get a summary where and which members the wind is actually generated now. I can click OK. That's all. Why it's changing, and I wanted to have 25 meter per second because I've changed the national annex, I think. So be careful with this. And so I click OK. It gives me a summary. And this is now already the separated view because this is activated still from our previous load definition. So you can display the surface loads as well. So and here you also get the ABCD definitions written in. When you display it separately, you get the member loads. Let me check something. We have used, yes, we set the wind on side AB. So the wind is blowing in X direction. Okay. We also need to define some wind that is coming from the silo. And these are horizontal loads, nodal loads again, of course. So in the X direction. So I'm going to define some new nodal load. And this time it's an PX that I'm going to define. It's 1.3 kilonewton. This is something you have to calculate yourself depending on your area where you're based on. And okay, and I'm going to define this on the same nodes as I previously did with the impost and the sulfate. Okay, I confirm this. And because of the silo's height, it's not only giving us a horizontal load, the silo tries to turn over. So we have to define some nodal loads up and downwards in the Z direction as well. So when we select this nodal load, I just double click on this one now. I also going to define a PZ, which is -4, so a load which is pointing upwards. And on the other side here, this nodal load, we need to define an PZ, which is pointing downwards. So this is us done with the wind in the +X direction. And now to save, again, a lot of work, we are going to copy this load case again, the same way as we did with the sulfate and the imposed loads. So I click on my wind in +X and I'm copy the selected load case and create a new one. I rename it into wind in +Y direction. The category is the same, so I confirm and the loads are staying the same. I can double click on the generated load. And what I need to change, the area stays the same. So the base geometry, the roof geometry, the category, the wind velocity, everything stays the same. The only thing we have to change is the direction where the wind comes from. So it's now blowing in the Y direction, BC. It's already noticed here, these loads need to be generated into the load case 4. So everything else is done and we can just confirm this dialog. You see now that the main direction is in the Y direction. Okay, we also have to change the nodal loads. So we don't have loads in X direction. We have to change this to Y, and we also have to change the vertical loads. So what we can do is we are going to the the table again that I've mentioned earlier. And now you see already that the nodal loads are separated because they are not identical anymore. So some of them have vertical loads. So you have on node 35 and 38, you have the horizontal px at the moment. We have to change all this over to py. You can just use the Control X and Control Copy from your keyboard. Say yes, and just enter a 0 here quickly. So now all the loads are py and not px anymore. But we also have to change the nodes because now the vertical loads need to be assigned to the node number 35 and the node number 38. So I'm going to change this to 40 and 41, having horizontal loads only. And I'm going to change this to the node number 35 and this to the node number 38. And you see what happened. You have, when you click on the row in the table, it gets highlighted in the main graphic. The node number 40 and 41 have horizontal loads only. The node number 35 is the one with the vertical load upwards, and the node number 38 having a vertical load downwards. So we defined all loads that we need. We defined 4 different load cases. Load case 1, 2, 3, and 4 for the wind, 2 and what happens now if you need to change something in your model? What happens especially with the generated loads? To show you this, we are going to change something in the model. We will enter 2 more small members. And I want to emphasize that you really have to double check your generated loads. Because this is I changed to the solid model again. This is an U-shaped member here. I'm going to define 2 additional small members, so just the angle cross-section members here to give it more hold because it's rotating around the weak axis. So I'm going to create another single member choosing the L cross-section. It was defined earlier, so I have just to select it from the drop-down, and it's a beam. And I confirm this and just define it from here over here and another one from here over here. Confirm this, and now we go into our self-weight load case, and you see that also this bracing member got some loads. That's what I don't want this in this example. It might be useful sometimes, but this is something, so there are advantages and disadvantages, and you can never say what's the right way, but what I want to tell you is that you have to double check your generated loads. So I just double clicked on the generated loads to open this dialog again, and I want to exclude these 2 members. So I remove the influence from, and I just select these 2 members and click OK, confirm this, and here you see how quickly the load changed. We have to do the same with the imposed loads. So I go to the imposed, I select it, I exclude the 2 members, confirm. So of course it happens very often in practice that you have to change and adjust your model later on after you've defined loads, and especially with the generated loads you have to be careful. I still think it's positive to keep all the information of the generated loads, but be aware that you have to double check them. So that's us now really done with all the modeling and all the load definitions. We are now going to create the load combinations. And just to remind you, in the general data, a bit slower, when you right click here on the steel platform on your model name, right click, you can open the general data here. And this is the place where we have activated the automatically generation of combinations. And we do it in accordance to the Eurocode, and we do not use the national annex today. So when we now open the load case and combinations dialog, we see the 4 load cases that we have defined. And we go now to the next tab, which is called actions, and we see 3 different actions: the permanent, the imposed, and the wind. And it automatically noticed the correct load cases. They are assigned to the action. This is because of the action category we have chosen. And in case of the wind, alternatively is selected here by default, and this is the correct one because wind in X and wind in Y will never act together. They are at either the wind in X or the wind in Y direction. So in the next tab, this is the combination expressions. It creates 4 of them, 1 for the ultimate limit state and 3 for the serviceability. 1 for characteristic, frequent, and quasi-permanent. We are only looking to the characteristic in this example. So you can always delete things, of course. You can delete actions, you can delete combination expressions to reduce the number and to adjust everything to your needs. So I'm going to delete these 2 combination expressions. So I have 1 for the ultimate and 1 for the serviceability. So here in the settings, because if you have a larger model and far more loads defined than I did today in the webinar, then you might end up with a huge amount of load combinations. And there are several options to reduce this. So you can, for example, use this checkbox here, reducing number of load cases. When you go in the tab here, there are some options you can use automatically things, and you can neglect, for example, load cases with less relevance in comparison to the most relevant load case. So you can define things here. Or another option is you could select leading variables. So this means I could say, it doesn't make sense in our case because we don't have many loads defined, but you could say, I'm only interested in having the imposed loads as a leading. So you could deactivate the wind, for example. This reduces the load combinations as well. Another way of doing it is you can individually define load cases that are either always acting together or never. So when you go in here, a table jumps up, comes up, and you can here define acting load cases. So either simultaneously acting load cases. For example, load case 1 can only act together with load case 3, and you have to do it vice versa. So if you want, it doesn't make sense in our case as well, but if you, for example, say, I want to have sulfate always acting with the wind, you have to do it vice versa in both directions. And this is one effective way to reduce the number of created load combinations. We are not going to use these tools today. And I will recommend at the end of the webinar, there's a video on our website available explaining these options very well and in a different manner again. So I will show you at the end of the webinar where you find it on our website. We are not using any of these options because we didn't define a lot of loads. So the next one, action combinations. So here you see what R-Stab is actually doing with our combination expressions now. So we have the sulfate only, we have the sulfate with imposed loads, then here the leading variable are the imposed loads, and then the other way around, wind only and leading wind. The same for the characteristic values. And these action combinations are now created to load combinations. So the action combination number 3 and 5, they will lead into 2 load cases. So we have 5 action combinations and end up with 8 load combinations. So you have here either you have the load case 3 and the load case 4. This is why you get 2 load combinations here, representing the action combination 3. Okay, and because we have switched on the option result combinations as well, we get an envelope of all our load combinations. So 8 load combinations are combined in one group. I show you what it actually means. Down here is a button where you can see the formula behind the combination. So when we open it, it tells us combination 1 or to combination 8. So it's doing an envelope of combination 1 or combination 2 or combination 3 and so on up to combination 8. So it's an OR combination. Okay. This result combination is very important for us in the next webinar because this is the one we are going to use for this design when we use the RF Steel Eurocode 3 add-on module. So this is the final result combinations that you are going to use for any design. That's us done for the first part of the webinar, and I'm going back to my slides. So this is what we did today. We modeled the steel construction, we defined some loads, and we did automatically generation of load combinations and result combinations. Next week, we go ahead with the same structure and we will perform a stability analysis using the module RS-BAC. This is the add-on module for AirStab. And I will show you a different model, which is then already, it's ready-made then next week. And we are going to use the RF stability, which is the add-on module of RFEM. So they are similar, but there are a few differences. This is why I'm going to show you both. And we will manually create imperfections, and we will also automatically determine some imperfections using the add-on modules RFIMP for RFEM and AirStab for both. And finally, we are using the module RF Steel EC3 or Eurocode 3, including the warping torsion and the plasticity analysis, and we will perform a steel design for our steel platform that we've modeled today. So please register for the next webinar if you like to see it. So this is our website, www.lubal.com. And you can always write us an email. You can contact us by phone. And as promised, I want to show you some more information about previous webinars and the video I have mentioned. I want to also invite you to an upcoming event, which is the and Fair Trade in Munich, which is just going to be held in end of November. And now we are having a look to the website, and I show you where you find the webinars. When you go to support and learning, you have the webinars here, and you can always watch our webinars. Even if you did not register for it, you can always watch it or download the webinars, and there are many topics covered by our webinars. And the video I've mentioned about the load combinations, you find this again, support and learning, and then underneath here is the link to videos. And if you just search for combination, you get this video here. This is what I mean, the RFEM 5 AirStab 8 combination video. So if you never really did some load combinations automatically and want to know how to reduce your number of load combinations, then this is what I recommend you to watch. So I thank you very much for your attention, and hope to welcome you again next week. Many thanks. Bye-bye.